In special relativity, we are dealing a lot with 4 vectors. But what exactly is a 4 vector? A 4 vector is an object with 4 entries which get transformed and changed in a very special way after we change our frame of reference. More precisely, a 4 vector transforms like a 1-0 Lorentz tensor under a Lorentz transformation. Now this might not seem helpful because it sounds like the famous example, a tensor is something that transforms like a tensor, but after watching this video you'll see that this is actually a really good definition. So what is this special behavior under Lorentz transformations? Let's assume that this thing is a 4 vector containing the elements a, b, c, and d. If we switch to a frame of reference s prime that moves with a velocity v with respect to our initial frame of reference s, the new values a prime, b prime, c prime, and d prime should be given by multiplying the matrix lambda onto our initial 4 vector. In index notation, this can be written as something prime mu equals lambda mu nu something nu. Now we can choose any values for a, b, c, and d. But if we choose time and the x, y, z coordinates, then yes, this is a 4 vector. Because under a Lorentz transformation, they change like this, and this is consistent with the matrix multiplication.
Another example would be the electromagnetic current density, J mu.
Here we have the charge density and the 3 components of the electric current. Their transformation behavior, when changing frames of reference, also agrees with this result of the matrix multiplication. To give you a counterexample, let's consider this thing. First, the x-coordinate, the momentum in z direction, the object's mass, and finally its velocity in x direction. This looks like a 4 vector, but is it? Let's check by looking at how it transforms under a Lorentz transformation. Now, this is how those properties should transform independently. But if we multiply the Lorentz transformation matrix onto this thing, we get some strange relations that don't agree with our previous relations. Therefore, this is no 4 vector. Another example would be a spinor, which is the solution of the Dirac equation and also has 4 components. Very often, various lectures and textbooks introduce 4 vectors and spinors within a short time frame, so there's potential for a lot of confusion. However, the transformation of a spinor under a Lorentz transformation is determined by a matrix S, which is connected to lambda mu nu but not equal to it. This means a spinor is no 4 vector. And that's pretty much it for this video. Thanks for watching.